Okay, where is it? Is it this one? Wait, I'm sharing my screen. Okay, so I check my e-learning still. There is Murad Abdullah 12 day didn't assess e-learning. Turkey 5 day didn't assess e-learning. Yusuf Madi 1 day 9 hours didn't access e-learning. Okay, so this one is like more than 24 hours. Didn't it's I don't know if you miss the test or if you miss something important information. It's because your own commitment. Okay, I don't know. Okay, I don't want to waste my energy. I just focus on student that want to learn. Okay, so okay, so this is chapter 6 part 1, and part 2 is actually compiled into one slide. Okay, so I just do a review today because we already touch it in detail in the recorded video. So please watch the video. Okay, here week 13 chapter 16 part 1. Okay, so I don't know. Maybe this one is maybe not the entire section 4. Maybe section 3 already start to watch because they also have the links. So I don't not sure who watched and who didn't watch. If you watch, you get the knowledge. If you don't watch, all the best. Okay. So chapter 6, part 1. Okay. I did my part already. Okay. I can force student if they don't want to even watch. Okay. So here there is a lot of type of filter response. Okay, if I not mistaken, during my time we study more than two types. So means that maybe your syllabus is made more simpler, I think. Okay, during my time, I think we study also a different type of. I mean, we study in detail. Okay, so means that your syllabus made simpler. You only study about this Butterworth and Chebyshev. Okay, last time I think I study also Basel. Okay, so uh, yes, in a good way you maybe a higher chance to score because less syllabus, but in terms of knowledge maybe will be much lower lah because you learn less. Okay, you learn less. Okay, I don't know whether this is a good or not. Maybe student will say I'm scoring A, but maybe yes, good, but I mean we don't teach all. I don't know why they make it simpler. Okay, never mind. Okay, so categories of filters, they actually there's two types. This is the fundamental, I mean the basic one, which is low pass filter and high pass filter. For the band pass filter and band stop filter, actually you can actually see it's like a combination. It's a combination of uh, either combination of low pass and high pass filter. That's why you have two cutoff frequency. Okay, it's just like combination. Okay, and then I've been explaining to you as well. Okay, in the recorded video, this is your cutoff, and this is a 3 dB drop. Okay, 3 dB drop. This one is a factor of 1 over square root of. Where's my calculator? When? Okay, so 1 over square root of 2 is equals to 0707, I think. Okay, and then 20 log of this, you get negative 3 dB. Okay, so I hope you know how to get this. How you get this 3 dB. Okay, 3 dB drop. Okay, this is your cutoff, and this is your cutoff frequency also, but this response is for the high pass filter. Okay, so this is the band pass filter, band stop filter, like I told you guys just before yesterday, I think, and also in the video. Okay, this it is made by this low pass filter and high pass filter individual. Okay, so this is just like combinations. Okay, and then this is filter response. Okay, the ideal filter you will have a gain of 1, and the bandstop you will have totally gain equals to 0. Okay, so the practical filter, however, we have bandpass with any constant value in dB, and bandstop not equals to 0 because we not totally have like wait, how I make it. Okay, so because in the ideal filter, we have totally drop, something like this. Okay, sorry, totally drop. Okay, but in practical, no, we actually have transition from here to here. Maybe we have transition. Okay, so we don't have totally gain equals to 0. Like here, totally gain 0 because sharp cutoff and then totally flat. However, in the real life practical filter, we have some value, which is not always means that it's not always equals to 0 directly. So it's like just like transient. Okay, and then this is the ideal filter response. Okay, ideal versus the practical. Okay, this one is the high pass filter. Okay, so with the green is actually the ideal, and the red is actually the non-ideal, which also we call as a non which is practical. Okay, practical. So this is a band pass filter. Okay, this is the band stop filter. Okay, band stop filter. So I hope you guys can okay, differentiate it. And then we in this chapter only study about Butterworth response and Chebyshev response. Okay, filter response actually the complete word. Okay, so you have Butterworth blue and Chebyshev black. So if you see there is actually advantage and disadvantage, for example. Okay, so if the question maybe if you want to have a faster roll off is actually like this. How much is faster change to, you know, uh, I don't know how to describe, but you can see like this one. This one is having faster roll off because you can see the gradient is steeper. So this one it have faster roll off. This one has a slower roll off. You can see the gradient is less steeper. So actually, for example, for example, if the question can be anything. For example, if they want a and filter fast with response close to sharp cut off, which kind of filter which is the best? So maybe Chebyshev, because you see Chebyshev has faster roll off, it's more mimic the ideal filter. However, what is the weakness of Chebyshev? We have ripple. In Butterworth it is flat. In Butterworth the flat response here following the ideal. Okay, and the Chebyshev didn't. So I mean, when you in life, right, you cannot have everything. So you take this one, you lose this one, something like that. Okay, so both of them have their own advantage, disadvantage. Okay, so you have this as a transition band, like I told you. This is your pass band and this stop band. So this A maximum is actually the rippling difference, ripple difference, you can call it. Okay, this one is pass band gain, this one is stop band gain. Okay, so the design process, you need to know this type of response. Which one? Which one question are talking about? Which one actually the filter response about? Is it Butterworth or is it Chebyshev? And after that, you need to know the cutoff frequency. Maybe you determine, depends on the question. I cannot mention specifically, but at least there is this information. Cutoff frequency, pass band gain, or attenuation, stop band frequency, or stop band gain attenuation. So this one is either given or you have to find. But this information is needed, something like that. Okay. Then you need to find your transfer function. Given here is Hn. What does it mean? What does it mean? HNS? Anyone? Why is not Hs? Why is HNS and not Hs? What is N here? Anyone know? Okay, B key is correct. This one is normalized. So this is normalized mean it is not the actual transfer function. You need to de-normalize. Okay. So that's why in appendix, how I find the appendix? That's why the appendix here, I think. Okay. The appendix, wait. This is the chapter for the appendix. I mean for the filter, filter characteristic, table E, and then table F, your analog filter, and this is your Butterworth, okay? Chebyshev, Butterworth, and then you need to do, this one is the normalized, okay? It is not the real value, it's normalized, okay? That's why you have omega Sn here. How to make it bigger? Okay, so Sn, n showing is normalized, means not the actual value, okay? And this one is circuit transformation for Chebyshev filter. If you have low pass filter, it look like this. Okay. If you have capacitor or this one, oh sorry, this one later. We on sorry, this one later. Okay. This one. Okay, where you actually will transform the normalized, the normalized. For example, if it's low pass filter, you need to replace S with S over omega C. Okay, this is in my video. I think yes, it is my video I teach. Okay, I remember because I'm struggling while teaching with my coughing. Okay, so here, okay, here is normalized. You need to denormalize, and then circuit realization. You need to realize the circuits. Okay, I think this one is Chebyshev. I mean this part. Okay. Filter response, there are two types, Butterworth transfer function and Chebyshev transfer function. So Butterworth is this transfer function, 1 over BNS, and this is the things, polynomial. You can look at the appendix. Okay, a n minus 1, s n minus 1 means the next one is a n minus 2, s n minus 2, and so on until you get 1. Okay. And then there is a Chebyshev transfer function. I want to touch this later on, okay? Later on. So this is the magnitude, okay? To get the magnitude is 2 over 2c, and there is here 2n. So let's say you get, I don't know when you solve later on, right? Let's say you get 12. Means the order of the filter is 6 because 2 times 6 equals to 12, okay? So filter response for Butterworth, okay. So we have orders, okay. Orders n equals to 2, n equals to 3. From the appendix, this is the order, okay. Order 2 you have A1, order 3 you have A1 and A2 having value, okay. So the same for this, okay. So if you see, if we have much more order, higher order, will have faster roll off. Okay, faster roll off means the gradient become much steeper. So if you see from the ideal response, this is the ideal response. Okay, ideal response you want to have to be like sharp cut off, but in real life we cannot have that. So maybe the better is the faster roll off will be give the more steeper curve, and then more straight look like curve. So that's why the more the order, the better it is. Okay, the more it mimic the ideal filter response. Why I explain this, because the question can ask anything. Maybe in your opinion, what if order like this? What can you describe? What can you, in your own understanding, why is this? Something like that. That's why I'm talking also like this, even though you can see, but maybe you cannot extract the information. Okay, so it means that the higher the order the filter, the better it is in terms of the roll off, because it is much faster, okay, and much steeper, and it more mimic like an ideal filter. Okay, so this is what Chebyshev response. Okay, this one later. This one later. Chebyshev I cover later. Okay, so if you see this is what I told in the recorded video. Okay, we have a passband roll off, and roll off is how we see it. How we see it, the more steeper it is, the roll off means much faster. Okay, so like this one has slower roll off, this Butterworth. Okay, but it have a good flat passband, flat, right? And then how about Chebyshev? It has a faster roll off, good, like almost like closer to eye filter, but it is the disadvantage is it have ripple here. Okay, so if I'm not mistaken, we, also the name like for this is equal ripple filter response. Is it? Wait. Yes, equal ripple filter response. So if they say equal ripple filter response, mean what type of filter that you should be doing? Is it Chebyshev or Butterworth? If the question mention equal ripple filter response, what are they referring to? Is it Chebyshev or Butterworth? No answer. Are you guys still there? uh, so it's Chebyshev, huh? Okay, equal ripple. And then if they mention flat passband filter response, correct, Chinto, you are correct. If they mention flat passband filter response, if they mention flat passband filter response, it is Butterworth. Okay, it's just like the same. Vilina, sometimes maybe somebody call you Vil, maybe somebody call you Vilina, some maybe call you Lina, but it's still the same person. Just have a lot of name. Okay. So you need to know. Okay. And maybe the question mentioned later on, the system or the design engineer required to design a filter that have faster roll off. So you should know which type of filter they want. Means they want a Chebyshev. Okay. So this is the difference. Okay, which already covered in my chapter. Okay, in my recorded video. So this is the filter design. Butterworth is much more simpler compared to Chebyshev. Okay, that's why it is being compiled with chapter 6 part 1 along with the introduction. Chebyshev will require another part of video. Okay. So the first step actually, you need to always know the order of the filters, whether it is N2, N1, whatever. They can, or they will describe what is the order filter that they want, or maybe they will give, for example, maybe they give this value, maybe. Then you need to know how to compute the order of filter. Okay, that's why you are given appendix, even though the appendix given, but you need to know how to use the appendix. Okay, let's say the question didn't mention the order number, but they mention this parameter, then it's actually you just plug in, then you obtain your order. Okay, because the first step is actually always know the order of the filters. Okay, second, this one, you need to calculate the omega c. You will have like more than one omega c value, and then you need to find which omega c will produce which value of alpha, which actually fulfill the given specification. Okay, after that you need to determine the normalized. Okay, normalized transfer function means not the actual function transfer function, but normalized one. Okay, refer to the appendix. Okay, so you have this actually h and s. So if you write hs, it will be wrong because it is means that it is actual. So please bear in mind. I mean, please carefully see how you write. Because let's say you answer all correct. For example, Vilina, let's say you answer all this correct, and it's but you put it SHS. For sure, I have to cut mark because this one is not the actual transfer function, but normalized transfer function. Those that always do careless mistake in exam, you know who you are. Okay, so make sure because this subject signal they have a lot of subscript, superscript, polynomial, partial fraction, or many. Okay, determine the real actual. After that, only you will determine the real transfer function, which is HS. Okay. So this is the Butterworth filter design, which already covered in the video. Okay, so you need to, in any way, you need to know the end. You need, depend on what is the question about. Okay, because I cannot specify this is the step. No, I can only say the first step is to know the order. But how we going to obtain the order? Many ways. Depends on the information provided by the question. Okay. So, do I provide already chapter 6 exercise? I forget. Did I provide the chapter 6 exercise? Hmm, did I provide this exercise? This exercise? Consult a book. Okay. If there is no exercise, I will make it for you. Oh, this is final. Did I share this one to you? Oh, not yet. Okay, okay, okay. Okay, never mind. I will share it later. Okay, I will share it later. This link. Okay. Okay. Uh, so this is kind of question. Okay, I think I covered this in my recorded video. Okay, so you see, design a Butterworth low pass filter. So mention here low pass filter. Jangan gatal-gatal buat high pass filter ke apa kan. Jadi salah lah. So you need to design a Butterworth and low pass filter. Okay, and then given a pass band gain. Okay, given that alpha p between 1 and 0.91. So how they actually get this value, negative 1? Do you guys know how actually we get this negative 1? Do you guys know how we actually get this negative 1? There is reason why I'm asking question in the class, because question can be many things. Question in final exam can be tricky. That's why even is given here, you need to know where you get this actually. Or if given this, so how you get this negative 1? How you get this negative 1? Never mind, you can guess. If it's wrong, okay. That's why I'm here, lecturer, to guide you if you done it incorrectly. But do you know how to get negative 1 here? You guys know not how to make how to get actually negative 1? Yes, correct, Vicky. Okay, so you guys need to know how to, because question can be many things. I honestly said, question can be many things. You need to know actually this means what. This means what? This is, if this is decibel, this is what then? What we call this? If this is decibel, this is what? This is decibel, of course. This is what? What we call this? Linear. Okay. And then a stop band not to exceed 0.0316. So this is a stop band. So it's a alpha S. Okay. For omega greater than 20. So this is the step. Okay. You can watch the video again if you don't understand. I think I covered this also in the video. Yes, I cover. You get n is equal to 6. Let's say if you get m filter, for example, 5.4. Okay. 5.4. So it should be 6. Okay. Okay, this I teach it already. Yes, I teach it. Okay. Then you obtain, once you have finished obtaining your order filter, the next is actually you determine which omega C actually fulfill specifications, fulfill whatever they want. So because you later on you will in the end you have two omega C, which one actually? Okay. So for this kind of condition, okay, you see here, given spec of alpha P and given spec of alpha S. So for this example, we will choose omega C 11.187. This one, okay, because 11.87 it produce this kind of alpha P, and this one is alpha S, alpha P. So alpha S is correct because this one is below 0.036, and for alpha P, it is in range. Okay, we cannot choose this value because it is greater than 0.0316. Okay, this one mentioned in the spec, and it's not within the range for the alpha P. Okay, so that's why we need to choose this. So you need to make decision which value to be chosen and why, because the question can ask you why also, right? Okay, so this is the omega C. Okay, you ended up with 11.19 radian per second. Remember, it's radian per second, not hertz. Hertz is frequency. Okay, wait, I'm drinking. Okay, um, then after that you determine the normalized transfer function, and it's given 6. So you need to do this polynomial. Okay, until finish until 1. I think when I do it, maybe not enough space, but I think hope you understand. 4, 3, 2, and 1. Okay, and then after you actually obtain the normalized transfer function, you will determine the filter transfer function, high low pass. What is this? It's low pass filters. Okay, then okay, so that is actually the review for the today. Okay, just very short, around 30 minutes, because we have covered it in video. I don't want you to be you means that